Hello everyone, and welcome to episode 1 of Particles in a Box. Today we're going to be taking a look at the International System of Units. So when deciding what to do for the first episode, right, I was kind of thinking back to, okay, if it was my first day of AP Physics or my first day of college physics, what would I have wanted to learn that day, right? Well, a couple of things came apparent right away, as I kind of figured out what I didn't want to do on the first day. Was a whole lot of like technical math or like anything like too philosophical about like what is physics or like what is chemistry, like what is math. That's a discussion for another day and farther down the line. But I feel like the International System of Units was a good way to start off because you're going to be using these units throughout your entire scientific career journey, however you want to describe it. And there's some interesting tidbits and like factoids that you can learn along the way. So if it's your first day sitting in class, being able to learn a couple of unique things that maybe some other people don't know, or just something that you maybe find a little bit intriguing, that's always nice. And then it can also like give you a preview of topics that are going to come up farther down the line. So with that being said, International System of Units. So what we're going to be doing here today, covering the SI system, System International. If you are French, I'm sure I didn't pronounce that right, but if you're French, let me know. We're going to introduce a little bit of the history behind the SI system and how it's changed over time, and then mention some of the scientists who units are named after. At the end, we'll talk a little bit about like alternative systems and alternative units. And then along the way, we'll cover some misconceptions and things that some people get wrong about what SI does and does not do. So the basics. There are 7 base units. We'll be diving into those base units one by one and looking into how they're defined and why they're defined that way, and look at some past definitions and how they've changed over time. Each of those 7 base units are each defined by a fundamental constant. There are 22 named derived units. So these are mostly named after people. A few of them aren't, but I'll briefly go over those. As we move along in the show and the units start popping up, I'll go into a little bit more about the people and the scientists behind those derived units, but I'll just kind of briefly talk about those today. There are prefixes, so you have your kilos, your decas, your decis, your centis, your millis. Right, there's prefixes to help scale units. There are many unnamed derived units, so there's like derived units that are named, but there's also plenty that are unnamed. I'll briefly talk about those as well. Again, we'll go more in depth as those units pop up throughout our journey. Metrology is the study of measurement. There are actually people that are metrologists, where they specifically like study how measurement is made and how it's done. And they just specialize in this field, which I thought was interesting. And the SI system was last updated in 2022. Every 3 or 4 years, there's a conference. I forget exactly what it's called. It's like CIPM or something like that. There's an acronym for it. But they talk every 2, 3, 4 years. They get together and they discuss, hey, do we need to update any definitions? What's going on in the world? Do we need to make any changes? In 2019, there was a really big overhaul, as you'll kind of see as we start talking about some of the units. But that is just kind of a little bit more in-depth overview. Here to start. So first, prefixes. So there are 24 named prefixes. The last update was in 2022, where they added these quita, rona, quecto, ronto definitions, which makes this like a massive scale nowadays, which is crazy. Like I remember like when I first started like looking when I was in high school at these, they were only at like yoto and yakto, and even those were like huge and like super small, and yeah, there's a lot going on. But with that being said, right, I mean your millis, your centis, your decis, your decas, your hectos, your kilos, right, those are the main ones that you'll encounter, right? Occasionally you might come across a mega, giga, or a tera. Especially when you're talking about like data drives and like terabytes and things like that. But you'll encounter those quite frequently. Micro and nano, you'll also kind of encounter semi-frequently when you're talking about like electrons and nuclei and like molecules and small scale things. Occasionally you'll see a femto or a pico. That's pretty rare though. We don't deal with those very often. And then we don't really deal with any of these ones down here like the super high range. I mean, these units that are at these extreme ranges are mostly for like specialized fields where they're trying to get like the absolute maximum precision and accuracy. I remember reading an article a few years ago about how they like first made something that could dispense a zeptoliter of water, which was just like which is just interesting. It was interesting. But like that just shows like how specialized and how small and how large some of these prefixes can be. But like I said, right, it's kind of like the middle range here that you'll see most of the time. You definitely don't need to go around memorizing these, especially at the extreme ends. But it just definitely is something that you should be aware of, and can be a little bit interesting. So base units. So there's, again, like I said, there are 7 base units. Each of them are defined by a constant. If I can get my thing to move out of the way, that would be very nice. Okay, there we go. So if you look down here on the bottom left, I got a little bit of a diagram here. This diagram shows how the different fundamental units relate to each other. Okay, so like right here, we got the second, right? And the second is defined by this constant, which we'll get to in a minute. But then it's got arrows showing how the second is actually used in the definition of other base units, which might sound a little bit strange. Like, how can something be a base unit if it's dependent on another unit? And it can be a little bit strange at first, but hopefully as we go on, you'll start to understand why that is. So first up we have the second. If we go back right here, right, you can see that 1, 2, 3, 4, 5, 6 just 5. Yeah, no, just 5. Sorry, yeah, just 5. So the meter, the amp, the Kelvin, the Candela, and the kilogram all depend on the definition of the second. So a second is a very important base unit, and it's one that we are very familiar with in our everyday lives. Okay, so the second is where we're going to start off. So currently, the current definition of the second is the unperturbed ground state hyperfine transition frequency of the cesium-133 atom is defined to be 9,192,631,770 hertz. Okay, so a lot of words and a really big number. What does this actually mean? Okay, so first of all, hertz is 1/2. It's a measure of frequency. And this definition was accepted in 1967, and there's been minor wording changes ever since then. These wording changes are related to, do you account for gravitational effects? Do you assume that the cesium atom is at absolute zero? Lots of like high-level technical stuff that is a discussion for another day. So this is a frequency of light that is emitted. It's a form of electromagnetic radiation, just like light is, that corresponds to a wavelength of 3.26 centimeters. So you can't actually like see this emission with your eye, but atomic clocks, which we use to measure time, can detect this frequency. And so since this transition has a specific frequency, it has a specific number of periods, and you can count how many periods that wave has. And once you reach enough periods, then that is 1 second. And these clocks are super accurate. It's honestly, again, it's kind of a discussion for another video on how these clocks actually work. But what about this hyperfine transition, right? What is that? Well, a hyperfine transition is the interaction between nuclear and electron spin, okay? This is not an episode on quantum mechanics, so we're not going to go more in depth as to what a hyperfine level is. If you know more about quantum mechanics and magnetic fields and spin, you can do some Googling, you can find out a little bit more. But just to leave things simple for everyone watching, it's just a relationship between the spin of the atomic nucleus, where the protons and neutrons are, and the spin of the electron, which is orbiting around the nucleus of an atom. The reason why we use a hyperfine level is because it's more resistant to environmental effects. Other quantum mechanical structures like fine structure are subject to changes in their emission frequencies based on the magnetic field. So Earth has a magnetic field that does slightly vary depending on where you are. So if we were to use like fine structure, for example, then we would have problems with a exact constant, as that constant would change depending on the magnetic field where your location is. And the idea behind these base units is that you want to be able to apply the definition anywhere in the universe is the goal. And having the magnetic field dependence would throw that out the window. So that's why we don't use something else, and we use this hyperfine transition. This was not always the definition. Like I said, it came back around in 1967, which, to me, not having been around for that long, seems like a long time ago, but it used to not always be the definition. So in the past, it used to be defined as based on the tropical year. Okay. And so what is a tropical year? Well, it's the year that you think of. It is a short way of putting it, right? Like your 365 day year, right? It is a tropical year. It's technically the time it takes to go from equinox to equinox. So like you have like the vernal equinox in the summer. No, you actually do not have an equinox in the summer. That is a solstice. Ignore what I just said. But you have the autumnal equinox in the fall or autumn, and then you have the spring equinox, which I'm forgetting the technical name of at the moment. But you have an equinox in the spring as well. So if you just go around and say, okay, you're in March, right? Okay, you have an equinox, and then how much time does it take to get to the next equinox? And this is not the best definition because the tropical year is not very constant from year to year. As you know, the equinoxes shift a little bit from year to year, and the exact timing changes and the exact day can fluctuate. So this wasn't a very good definition. And so I've got this diagram down here on the right, where it talks about the difference between a sidereal day and a mean solar day. And so tropical year is based off of mean solar days, right? There's approximately 365.25 something mean solar days in a year, right? But there's also this thing called sidereal days and sidereal years. So the difference here is that a sidereal day is Earth's rotation due compared to the fixed stars, right? So it shows how in this first image, right? Okay, you have the star that would be directly behind the sun, right? And then as the Earth moves along its orbit, right? So it's moving along its orbit, but it's also rotating at the same time, okay? And so what ends up happening is that you end up facing the same direction as that fixed star sooner than you end up facing the sun. And it's like, well, at first, right, this can be a little bit confusing. It's like, well hang on, how does this work? What ends up happening is because Earth is rotating around the sun, as well as rotating about its own axis, it actually has to rotate about an extra 1 degree to have the sun in the same location a day later. And so that's why there's this subtle difference. Is that it takes a little bit more time to get the sun back in approximately the same position. It's not exactly the same position, but approximately the same position a day after than it does to rotate the same distance compared to that fixed star. So if you're wondering why there's 360 degrees, why we use 360 degrees, that's because it's 365 days to go around the sun, and it's approximately this 1 degree difference. 365 is about 360, right? There's about this 1 degree difference that the Earth has to rotate an extra little bit to get that sun in the same position to get through that solar day. I mean, almost all of us use solar days unless you're an astronomer. You don't really care. You don't really care about sidereal days, but there is a difference. That's why they used to have to define it specifically as a tropical year. And because of like wobbling of axes, precession of the equinoxes, other gravitational disturbances, right, the tropical year is not a good way to measure to measure things. So the future of the second. The future of this is the only base unit that actually have a future slide for. Most of them I just have like what the current definition is and what it used to be in the past, as I don't really see most of the base units changing in the future. But the second is one that might actually have a redefinition coming up within the next decade or so, and that's because there is a new type of clock called a optical clock. That are even more accurate than the cesium clocks that we have in use today. They're still kind of in the developmental stages, which is why they haven't been accepted yet, but they have been shown through multiple experiments at this point that they can be as accurate and even more accurate than cesium clocks. So currently strontium clocks hold the record. These things are accurate to billions of years. They can be accurate to within 1 second longer than the age of the universe, which is crazy to think about. Cesium clocks can be like hundreds of millions of years, which is still a really long time. But these ones are even better, which is, 100 million years is already a long time. Billions of years, yeah, it's just crazy to think about. The reason why these are nice is because it's easier to measure optical frequencies with current equipment than it is to measure like radio or microwave frequencies, which kind of makes sense. We can also see optical light, so that also is kind of nice. And so these things are so precise that you can measure a 2 centimeter change in altitude from the center of the Earth with one of these clocks. That's how precise it is. So, 2 centimeters, right, is not a lot, right, for people with imperial unit rate. That's a little bit less than an inch, about like 3/4 of an inch or something like that. So that's just crazy to think about. Another problem with one problem with optical clocks right now is that there's lots of different forms. Some of them use strontium, some of them use other elements. Like ytterbium is another common element that's used. So in order to get the redefinition approved, right, scientists would have to settle on a specific element that they want to use, right? And then optical clocks are a little bit more complicated than just like the hyperfine transition definition. There's a little bit more going on that's beyond the scope of this video. So there's still some work to be done on this, but I definitely can see this change going through in the next 10, 20 years as the community kind of comes together and decides on an accepted definition. So going on to the meter, the good old meter, it's just a unit of length, I guess. Currently, the definition of the meter is the distance that light travels in a vacuum in 1 over this number of seconds. I don't want to butcher it, but that's the number of seconds. That's the amount of time. So what this really does is, in practice, it sets the speed of light to a constant 299,792,458 meters per second. Okay. I put this approximation that's approximately equal to 3 times 10 to the 8th because if you are really doing any like homework problem or really doing any sort of calculation for the most part, this number is so close to 3 times 10 to the 8th. We just plug in 3 times 10 to the 8th, right? That way you can cancel out exponents and it makes doing hand math a lot easier than using this number. You might ask, why is it not exactly 3 times 10 to the 8th? Well, it's because as they change definitions, right, you need to be close to the previous definition. Otherwise, all previous research that's been done is basically invalid. Right? If they were to round this to 3 times 10 to the 8th, well, that's too big of a difference compared to the previous meter from, I think it was like 50 years ago, right? That'd be too big of a change. And so it would cause all sorts of problems in research, and it would just cause a lot of problems. So that's why they don't do that. But that's the number. This definition was accepted in 1983, and laters helped a lot in this and whatnot. So in the past, there's been a few different definitions of the meter over time. It used to be 1/10,000,000th the distance of the meridian line from the North Pole to the equator through Paris, France. France holds a lot of artifacts related to SI, and were kind of instrumental in creating the SI system. So they've got a lot of influence. That's why they chose Paris, France. Paris, France is also pretty close to the like 0 meridian line, which also helps. So that was in 1795. In 1889, you know, this distance, of course, is hard to measure. You know, continents do move. It's just like there's not like they didn't have satellites back then, right? So it was very hard to measure this distance. Not to mention that Earth isn't a perfect sphere, right? So yeah, there's definitely a lot of problems that quickly become apparent when using this definition. In 1889, it was defined as the length of a platinum iridium bar at the melting point of ice at atmospheric pressure and supported by 2 rollers. So, oh gosh, okay. So down here on the bottom right, this is just one end of that platinum iridium bar. You need to specify a temperature that's at, because thermal expansion is a thing. So if it's at 100 degrees Celsius versus 0, right, that's going to cause expansion and shrinking of the bar, which will change the length. So that's a problem. Atmospheric pressure, pressure can also affect the length as well. Not as much as like thermal expansion, but it can still have a small effect. And then supported by 2 rollers, so that doesn't like bend down a little bit, right? Like that bending down makes it not completely straight. So that was a little bit of a problem. So these 3 things, the fact that you have to define a temperature, a pressure, and then like have it supported, right, kind of shows why this is definitely not a super great definition, right? Not to mention that's just like 1 bar in some vault in France, right? That's like not easily accessible. When we get to the kilogram, you'll understand more about why like having these artifacts is a little bit of a problem. But yeah, just not great. So then in 1960, it was defined to be a large number of wavelengths of the 2p to the 5d transition in the krypton 86 atom in a vacuum. So this is pretty similar to the hyperfine thing, except it's not hyperfine. It's an actual electron transition moving between energy levels and different orbitals in the krypton atom. The wavelength of this is about 606 nanometers. Which actually is in the visible range. I'm trying to remember what color that would be. I think that's like blue, if I remember correctly. Yeah, I'll make sure to double check this, and you'll probably see a text pop up telling you what color this is. So yeah, I mean, this was definitely is better. Again, this decimal point definitely doesn't help out a ton. But with the speed of light being constant in the universe and the development of lasers, right, it made sense to fix that constant, which is ultimately why they ended up changing it. And this was only like a definition for like 20 years, right? Like 100 years almost another 100 years, and then within like 20 years they changed it. So that's interesting. So that's the meter. So next we move on to the kilogram. Okay. And the kilogram is an interesting unit. It has a lot of history behind it because it was the last unit to have a physical object as a definition. So like I talked about like that bar here, right, with the meter. Well, that hasn't been in use for 100 plus years now. A lot more recently, the kilogram was still defined as a physical object. It wasn't that long ago. And it's the only base unit to have a prefix. So it has kilogram here, kg, right? So it has the kilo prefix on it, even though it's a base unit. So the base unit is not the gram, it's the kilogram. So if somebody says, no, the base unit's a gram, the base unit is actually a kilogram. So that's an interesting fact. So currently, this was in 2019. So again, not that long ago they changed this. The Planck's constant is defined to be an exact constant in joule seconds. A joule is kilogram meter squared per second squared. So the definition of the kilogram depends on the definition of the meter in the second. And as we saw with the meter also depends on the second. So yeah, do with that information what you will. How to actually use the Planck's constant to obtain the kilogram? Again, that's way beyond this video. A lot of expensive and high-end equipment is used. They wanted to get this redefinition done earlier, but because of the complex nature and like the effects of gravity and heat and all sorts of environmental conditions, right? To get this much precision, it took a lot of time and it took a lot of effort and it took a lot of money. So this was definitely not for the faint of heart. So in the past, since 2019 is when it was redefined, until 2019, from 1889 to 2019, it was defined as the mass of a platinum iridium cylinder, which is not as big as you think it is, but it's just inside like a bunch of glass, vacuum sealed stuff, thermal insulation, and just to protect it from environmental effects. But it turns out that this created a lot of problems, to say the least. The first of which is that copies of the prototype had mass drift. Okay, so what they do is that there's the main prototype, right? Like, so with like the iridium bar, right, and with this mass prototype, right? They're stored in a vault in Paris, France. Okay, so how do we create like additional, how do we create an actual measurement device, like a scale or something that can measure a kilogram, right? If this is the one true kilogram that's stored in France. Well, the answer is that there have been copies that have been made, right? I think there were like 12 copies that were made along with the original prototype back in 1889, and they were like, one was sent to the United States, one was sent to Germany, one was sent to the UK. They were sent to different countries, okay? And then from those standards in each country, you can make some more standards, right? And then you can use those standards to actually like build a scale or build a measurement device that can detect 1 kilogram, right? The problem is that like every so often, they would bring all of these standards back together, and they would take the mass and see, hey, is 1 kilogram still 1 kilogram? And the answer was, well, no, not really, which is a problem, right? As you can look down here at this graph, right, you can see, okay, so at the inception, right, all of these were pretty close to 1 kilogram. There was a little bit of variation. You can't make everything exactly 1 kilogram, especially back in 1889 where they didn't have a lot of technology back then, right? Super hard to make 12 identical copies of something, right? So then, they brought them back together, like 50 years later, and they had discovered the masses were divergent. Most of them, it appeared, had gained mass, while most of them had lost. Well, a few had lost mass. Okay, and this is on the scale of micrograms. This isn't nanograms or picograms. This is micrograms, which is a relatively large quantity of mass to be gaining or losing. And so, then they brought them back together a few some more years down the line, and they had discovered, well, now only one mass standard over time has actually lost mass, while the rest have supposedly gained mass, right? And we're approaching 100 micrograms here. So this is a problem, right? These mass standards are diverging from each other, and so people, quickly started to realize, hang on, we need a better way to define the kilogram. And so that's what led to the huge effort to get the Planck's constant to define the kilogram. Another problem here, though, is that only relative drift could be measured. Since this is the one true kilogram, whatever the mass of this thing is 1 kilogram, right? You can't measure relative drift. So you can't tell, hey, has this thing gained or lost mass? You don't actually know because it is 1 kilogram, right? Like the mass of this thing technically, by definition, does not change, even though it seems like it has lost mass compared to everything else. We don't actually know because this is the 1 kilogram that actually existed. So again, right, not a great system, but with the technology limitations of the time, they did the best they could, and thankfully now we have a better way of defining what the kilogram is. So that's time, length, and mass, 3 pretty fundamental units that we're mostly familiar with in our everyday life. The rest of these units you may not encounter on your day-to-day basis, but nonetheless they are important. So next up we have the Ampere. The Ampere is a unit of electrical current. It defines the fundamental electric charge to be this very small value. This was established in 2019, along with a lot of other sweeping changes in 2019. So how this is realized is that the Ampere is a measure of electrical current, like I said. C is the unit for Coulomb charge. and that's a charge, and per second time. So an ampere is a coulomb per time, so it's the amount of charge that passes a point in 1 second. Okay. So the elementary charge is the charge of an electron or proton. Okay, this is the smallest fundamental unit of electric charge you can have. So 1 electron has this charge, and 1 proton has this charge, and all other charges that exist are a multiple of this charge. The ampere is named after Andre Marie Ampere, a scientist back in the 1800s. I'm pretty sure it was 1800s, who did scientific research. You might be familiar with Ampere's law. That is also named after this guy. Ampere's law is way down the line for a future video, but he is one of the guys that helped out. Okay, so in the past, the ampere, since from 1946 to 2019, was defined as the current needed in 2 straight parallel wires of infinite length, negligible cross section, placed 1 meter apart in a vacuum, would produce a force of 2 times 10 to the -7 newtons per meter of length. Okay, so we'll get to the newton a little bit later, but that is a unit of force. Okay, so actually there's something similar to this when I was in college. I wasn't like defining the ampere or like making ampere measurements per se, but I used like the same instrumentation. Right? So how this works is that you run a current through one wire, say to the right, and then the other wire you run a current to the left. Okay, what this does is that these wires are actually going to repel each other. Okay, and you can measure the force of that by placing some mass in this bucket right here. So you're gonna have a force of gravity that's pushing down on the wires, and if these wires are placed 1 meter apart and this much, and you have this much mass that corresponds to this much force, then the current going through each of these wires is 1 amp, which is pretty neat. Again, this isn't like a fundamental constant per se, right? Like the fundamental electric charge. This does highly suggest like how you would like actually measure 1 ampere and actually like determine that experimentally. Most of the other units that we've talked about, right, I've kind of been like, how do we actually like measure this? How do we actually find what this value is, right? Like experimentally, right? That's kind of beyond the scope. But this one, right, it's a little bit easier to understand. A couple of things that are related to this is that the constants mu. Oh boy, that is super bad handwriting. Let me try this again. Mu naught and epsilon naught. If you know what these are, you're in the know. If you don't, again, that's a topic for a future video. These used to be exact measurements. They had no uncertainty in their quantities because of this definition. And since they changed the definition to the electric charge, these now have some uncertainty. It's not a super big deal because these two constants combined can also give you the speed of light when they're arranged in a particular way. Again, that is for a future video, but just thought that I should mention that for those of you who might be aware. So moving on to the Kelvin. The Kelvin is a unit of temperature, and it is currently defined so that the value of the Boltzmann constant is to be exactly this value in joules per Kelvin. Okay, so we saw the joule a little bit earlier when we were dealing with the kilogram. The joule is now back in joules per Kelvin. Okay, this was again established in 2019 as part of the big redefinition. How you actually use this in practice to find the thermodynamic temperature, again, definitely beyond the scope of this video. Alright, so the definition in the past of the Kelvin used to be the triple point of water is defined to be exactly 273.16 Kelvin. So what is a triple point? It is the point where water vapor, ice, and liquid water can all exist at the same time. Not super practical in everyday use. But because it involves like a change in pressure, it's not atmospheric pressure where this occurs. I'll put that up here, whatever the pressure is, so you can get some comparison. But one thing I wanted to bring up in relation to the Kelvin is the difference between Kelvin as a thermodynamic temperature scale and Celsius as just like your normal scale, right? The thing about Kelvin, right, is that what do I mean by thermodynamic temperature scale? What I mean is that a Kelvin, because it's thermodynamic, can never be less than 0. You can never plug in a negative number in as a Kelvin. Okay, the scale is not defined below 0. What is the case, though, is that Celsius can obviously be negative, right? A degree Celsius is equal to Kelvin minus 273.16. This actual constant right here, which is pretty nice. So this actually turns out that this point right here, right, is actually at 0 degrees Celsius for water, but the pressure, right, is different. But Kelvin is defined in such a way that the change in 1 degree Kelvin is equal to the change in 1 degree Celsius. So how can you say that a Kelvin doesn't equal a degree Celsius, but you can say that a change in 1 degree Kelvin is equal to change in 1 degree Celsius? And that's related to how temperature is related to energy and heat. Heat is a measure of energy, and temperature is related to the energy distribution of particles in a substance. Okay, a little bit of technical jargon. Again, it's for another video, but for those of you who are curious, right? The change in 1 degree Kelvin is equal to the change in 1 degree Celsius, right? That's why you can just subtract off a constant and get to a degree Celsius, right? It's not like when you're going from like Celsius to Fahrenheit, where you got to multiply by like 9/5 or 5/9, depending on which way you're going, right? There's that multiplicative factor in there, right? But when you're converting between Celsius and Kelvin, there isn't. So if you have a formula that says change in temperature, right, or that has like a delta in it, or like a final minus initial of a temperature scale, you can actually plug in Celsius to that, right? The example that I'm quickly thinking off the top of my head is the specific heat Q equals MC delta T, right? Where you got the mass of your substance, you have the specific heat value, you have the change in temperature, right? And you have the change in energy right here. An example where this doesn't work, right, where there's not a delta T here, is in the ideal gas law. PV equals nRT. Right, this is an actual T, right? It's not a delta T, it's an actual T, so you can't plug in Celsius into that and get a right answer. Okay. So I just wanted to bring that up for those of you who are curious, right? This is a common misconception that a lot of people have questions about. Is when can I use Celsius and when can I not? Of course, the safe answer is always convert to Kelvin. If you convert to Kelvin, you can never go wrong. But sometimes, right, you know, if you're on exam, you're running low on time or whatever, right, you just want to quickly do it, right? That's when you can do it. When it's delta T, you can use Celsius. If it's just T, you cannot. So going on to our next unit, we have the mole. If we go all the way back to the intro slide back here, you can see that the mole is not dependent on any of the other units. It's kind of out here on its island by itself. So that makes it unique, unique in that respect. I did forget to mention, this is Lord Kelvin down here, also known as William Thomson First Baron Kelvin. This is a photo of him. Look at that beard, like, already a legend just for that beard. But this is who the Kelvin is named after. So the mole. Currently, it is defined as the amount of a substance of exactly this many entities per mole. Okay, so basically for every, so like if you have this many entities in something, you have 1 mole of that thing. Okay, if you have double this amount, then you have 2 moles of that thing. Okay, if you got 3 times this amount, you have 3 moles of that thing. Okay, that's where the entities per mole thing comes in. This was established in 2019, defined this to be Avogadro's number. And down here we got Amedeo Avogadro. His full name is much longer than this, but this is his colloquial name. And they define this to be exactly this number. In the past, it was defined as a system that contains the same number of entities as there are 12 grams of pure carbon-12. Okay. So this what is related to, like, if you take a look at a periodic table, right, below the element, right, it's got like the mass. I don't actually, is it mass number? I forget what it's called. But anyway, like if you have like carbon, right, it'll be like 12 point, like 0, 0, dump something, something, 1. I forget what the actual number is, but it's got numbers down there. It used to be that carbon 12, right, was, you know, just 12.0000000, right, where the mass per mole, or the mass in grams per mole was always 12, right, and then everything else was based off of that, and so you had like some variations and whatnot. It's complicated, again, beyond the scope of this video, but it used to be defined that way. Yeah. Well, I'll just leave it at that. I'll just leave it at that. So our last base unit, we have arrived at the Candela. When you bring up base units and you say that there's 7 base units, most people can get second, kilogram, and meter, right? Like pretty quickly, right? And then if they think for a little bit, they can normally come up with like Kelvin, or maybe they'll say Celsius, right? And then they might get Ampere. And then they might get mole, right? But most of the time, people do. Then they're like, wait, there's 7? Wait, should there only be 6? Well, it's because of the Candela, and the Candela is an interesting unit, and we're gonna have some fun with this one here. So, to begin with, we have the luminous efficacy of monochromatic radiation at a frequency of 540 times 10 to the 12th hertz is exactly 683 lumens per watt. So what is a watt, right? Well, a watt is a unit of power, okay? And the power is joules per second. So if you saw the joules in the few previous slides, this is a joule per second unit of power, right? What is a lumen, okay? Well, a lumen is a candela times a steradian. Okay, well, what is a steradian? We'll get to that in a future slide. It is a solid angle measurement. So if you're familiar with radians and degrees, it's sort of like that, except it's like a 3D version. Okay, and then when you break down the watt, you get you end up getting this when it's in the denominator. Okay, this was established in 1979. The current definition. Got a candle down here because the candela is based on approximately the brightness and intensity of one candle. Of course, candles vary wildly, but it is approximately that. Okay. So yeah. So a little bit more info. We're gonna dive into this a little bit more, so that we can get a little bit of a better understanding of what is going on here. Okay, so how do you actually find the luminous intensity, which is measured in candelas? Okay, well, what you have to do is that we're gonna throw up our first calculus warning right here. Okay, for those of you who maybe don't have a whole lot of calculus experience, this is gonna get a little bit mathematical. Of course, you're still welcome to follow along. But just try to pick up what you can and see what you can pick up. So what we got here, right, is that we have a constant, right? Our 683 from the previous slide. We have this phototropic luminosity function, okay? And we have the radiant intensity, okay? So the constant, right, we saw on the last slide, that's a constant, okay? The radiant intensity is just a measure of wattage, right? How much power is this thing giving off, right? So the best way to think about this is like if you have a light bulb, right? There's a wattage associated with that, right? That's how much like energy it's giving off per second. That is a radiant intensity, okay? But this phototropic luminosity function is a little bit more complicated, okay? So if we come over here to the top right, we have two curves. We got the green curve and we got the black curve, okay? So your vision is sensitive to different, is more sensitive to certain wavelengths of light, okay? So this green curve right here is the scotopic vision, scotopic, I hope I'm pronouncing that right, where that's how sensitive your eye is to certain wavelengths at low intensities, okay? So like when it's dark, for example, right? So from like 10 to the -6 to 10 to the -3 candelas per meter square, right? This is how sensitive your eyes are to certain wavelengths of light, okay? Okay, so yeah, so down here we have units, nanometers, and then to make things a little bit easier for you, right? Red is longer wavelength, so red is way out there, and purplish or blue is way down here at the shorter wavelengths. Okay, just so you can get a little bit of a bearing of like what am I actually looking at, right? And then if you look at right here in the middle, that's green. Okay. So this green line here, the scotropic, right? Low light intensity. This is how sensitive your eye is to certain wavelengths based on the peak up here. Okay. The black one is at higher light intensities, right? Like your main color vision, right? From 10 to 10 to the 8th candelas per meter. There's a little bit of a gap here because there's also like an in-between one, which is more complicated, makes the graph more clutty, kind of ignore that. So the max right here is at 555 nanometers. That's where the value is 1, okay? Okay, so one thing that I like to do here when we have a function that is kind of new, right, is I like to take out my graphing stuff and see if we can find out a little more about it, right? Like this is a new phototropic spectrum, right? And it looks like it could be like a Gaussian, right? It sort of looks like it could be like a Gaussian, but I had a sneaking suspicion that it's probably not exactly a Gaussian, right? Because I mean, I would imagine that like at each wavelength they would measure like your eye responsiveness, so it's got to be close but not quite. So I wanted to do some investigating. So this is Mathematica here. I really like Mathematica. It's a very powerful tool, and with that power comes a lot of responsibility. Okay, we'll talk more about Mathematica later as I use it in future videos, but it's a powerful tool. Okay. So the first thing here, right, citing my source, Hyperphysics, is where I got the data table for this, right? So I'll just kind of walk you through what I did and see what we can discover, right? So first of all, I'm just setting a variable here, and I'm importing my wavelengths from the data table, okay? And so then you notice I went from blue to black, right? That means it ran. That means that this W is now defined. It's a variable that has become a defined variable. And then what we have to do is we have to flatten. Mathematica is kind of known for being very finicky, right? Like if you look up here, right, it's got like bracket, 380, bracket, right? That means that like 380 is in its like own array, right? It's not, but it's also part of the bigger array, right? This just gets all the numbers inside of one array, okay? And you'll see why this is important, right? And then we go ahead and import my actual like weight data, right? So like what is the sensitivity at each wavelength? We do that. We want to flatten this as well. And so then we want to thread this together. So what threading does, right, is it's going to take 380 and it's going to pair it up with this first value, right, to create an XY pair at each spot, okay? And so what we're going to do is we're going to go down here and we're going to plot that data, okay? So that just shows you all the points, right? And as you can see, right, there's some kind of gaps in here, right, that I wish weren't there. I wish we maybe had a little more data, but you know, you got to take the data that you have and do the most you can with it. That's pretty common in like science and science labs, right? You just got to do the best you can with the data you have and the time that you have available. We don't have billions of dollars here to spend on experiments, unfortunately. So this is a resource function here. If you like, Mathematica has like a very good like documentation system, and you can go online, you can look up functions, right? What I wanted to do here is I wanted to find out what is like the average value of this function. And so what that so what this is doing here, right, is it's running the function, right? It's going to make a Riemann sum, right? It's some of you maybe has been a while since you've done Riemann sums, right? But since we don't have a continuous function here, right, we need to use Riemann sums to estimate the integral value of the integral of this function. So we're using trapezoidal method, right? If you were to put in right here, right, it should, yeah, right, it does like right justification, right? You can see how that looks a little bit wonky, right? And gives us a slightly different value, right? So we use trapezoids, right, to make it look a little bit more smoother, make it a little more accurate, right? And so then the highest wavelength value we have was 770, the lowest one we have is 380. We subtract those, right? That gives you about 0.27 as the average value. So somewhere right down here, okay? But I was really curious about was how does this approximate a Gaussian, right? So we come down here, right? We're gonna run a nonlinear fit. A Gaussian is not linear, right? So we're gonna plug that in. What we got here, right, is we have our data, right, our XY pairs that we have up above, and then we have a times e to the negative. So this is this is the Gaussian form, right? You have some sort of like amplitude adjustment, right? And then you take that then you raise it to a power, right? The normal form is negative x squared, right? But you need to adjust for that we're shifting the middle value here, right, is over at like 555, right? So we need to shift that. So that's why we have x minus b squared, quantity squared, over 2c squared. And c is the standard deviation. And so then what I ended up having to do is that you have to define a, b, and c as like, okay, those are constants that we're fitting to, right? I want Mathematica to go search through a bunch of values and see which ones are the best. But you kind of have to narrow down the range, right? What it'll try to do is it'll try to plug in like numbers from negative infinity to infinity, right? And giving it like a range of values to look between definitely helps out a lot, so that it can find a better value for you, right? It's like A, I know it's got to be close to 1, right? Like the maximum value of my function is 1, so it's got to be pretty close to that, right? B, right? I'm actually going to change this really quick, actually, because I think maybe I tried something different, but why is my, no, there we go. So we'll see if that changes that a little bit. And then C, right, the standard deviation, I was kind of guessing like, well, where is a third of my data? But like how far away from 550 is like a third of my data or 2/3 of my data? And I kind of was like, well, if we're going all the way down to here, that's probably about 3 standard deviations, right? So that's about 150. So about 50 for the standard deviations, it seemed reasonable to me, right? And then we're fitting to the variable x. You can do that. That fits the model, right? And then you can do it so that it gives you out a, you know, some random numbers, right? So again, right, it's about 1. And then we can come down here, we can plot it, right? So again, right, the A value rate is right about 1, so that makes sense. This value here, right, seems a little bit scary. We'll get to that in a second. Right, and the shift was about 560. So as you can see, right, when I plot this, right, it seems like it's shifted over to the right a little bit, right? It's not like, it seems like the peak's a little bit off. I tried to get this to move, and it just wouldn't move. So I'm not sure what's going on there, right? This might be a case of if you plugged into like MATLAB or something like that, right? Maybe you would have something slightly different. I'm not as experienced with MATLAB, so that's why I don't use it. But then we come down here, right? We have our C value. It's a little bit different than the one up here because I changed our parameters to fit a little bit. But if you plug that in, right, it gives you about 41. It gives you a negative value too, right? Plus minus square roots, all that fun stuff. But it gives you a standard deviation of about 41. Doesn't mean a whole lot per se, but I just thought, you know, and anytime I see a new function, I like to explore it a little bit. So, and this gives me a chance to introduce Mathematica, which is a tool that I'm going to be using not only for my research and like helping me with like problem examples, but also something that I'll show you guys for you know, graphs and all sorts of nice things. Right. So what this phototropic luminosity function is doing, right, is it's telling us that we are going to see something more dim of certain colors, right? So like if you have a green, right, that's going to appear relatively brighter as compared to the same source if it was purple, right? So it's trying to account for human vision sensitivity, right? Like watts, right, is just a measure of power, right? That's of energy over the entire electromagnetic spectrum, right? From radio waves to gamma rays, right? This function here is removing parts that we can't see and just focusing on the visible spectrum, right? So in order to get the luminous intensity in candelas, right, what you have to do is that you have to take this luminosity function value at each wavelength and the radiant intensity per radiant at each wavelength, and then you have to sum over all the wavelengths and from your source. Okay. And there's a couple of issues, and there's a little bit of an issue with this here, right? And that if you look down here at the bottom, right, I've got some math here. So let's explain what's going on, right? So this is an example of if you want to find the candelas of a light bulb, okay? So the conditions of this light bulb are that we have 2,000 lumens from this, we're going to use the example of a fluorescent light bulb. Oh boy. I think I'm going to spell fluorescent wrong, so I'm going to cut here and double check my spelling on that. Okay. So what we got going on here is that we have a fluorescent light bulb, okay? It produces 20 watts, and it has an output of 2,000 lumens, okay? So, first thing you might be wondering is, okay, how do we get from this equation over here down to this equation right here, okay? So, the radiant intensity per steradian, okay, is actually just this 20 watts over 4 pi, okay? That you just directly plug that in right there. Again, we'll get to why it's 4 pi when we get to the steradian slide down the road, but we have the total output in watts over the solid angle that's outputted over, okay? Now, what's this 2,000 lumens per 20 watts, right? Well, if you remember from the previous slide, that a lumen is actually a candela times a steradian, okay? So that's how we get from this thing right here down to lumens, okay? This middle thing is a dimensionless quantity, okay? It has no units. So when you multiply it by this constant out front, right, the units don't change on it. So you have this constant in lumens per watt, okay? That is actually your 2,000 over 20. And you might be wondering, well, hang on, how do we get from 683, this quote-unquote fundamental constant, over here to this 2,000 lumens per watt? Okay, and the answer is that this thing right here is an idealized constant. Okay, there is, from what I could gather based on my research, there is nothing that can reach this level of, I'm hesitant to use the word intensity because I don't think that's the proper term, but they can actually reach this efficiency, maybe is the better word, but efficiency is also kind of a measure of a different thing. Point is, this constant is idealized, right? And you're never going to really ever be able to get there with anything, okay? But the problem with that is if you know stuff about black body radiation, right? You know that, like the sun, for example, right? It peaks in the green, but it emits radiation throughout the entire spectrum, right? And so what the lumen is doing, this unit implies visible range, okay? So we're focusing on the energy and the light being outputted in the visible range, okay? We're ignoring large swaths of the electromagnetic spectrum, right? Like a light bulb, for example, especially incandescent ones, right, have a very small part in the actual visible spectrum. They release a lot of heat, right? They release a lot of infrared radiation, right? So that's not part of this lumen measurement, right? That's included in the watt measurement here, right? As the watt power measurement is over the entire electromagnetic spectrum, but the lumen measurement is not, right? So if we come over here to the bottom right, this was a really, I'm so happy I found this because it really explains well, like what's going on here, right? Is that we have radiometry and we have photometry, yeah, radiometry and photometry, right? Where radiometry deals with the whole electromagnetic spectrum, right? And it's radiometry, right? You might be thinking like Geiger counters and stuff. That's because like when things decay in like radioactive decay, right? They release like gamma radiation. They release all types of radiation that is invisible, right? So you need to be able to measure all that extra energy, and you need watts to do that, right? Photometry and these lumen and candela measurements, right, are for visible spectrum only. It focuses on what we can see, okay? So it does a good job here of saying like, okay, so if you're over all of the whole light bulb, for example, and you're non-directional, right, and you're making a measurement, right, well, that's called luminous flux, right, or radiant flux, depending on what you're doing. You convert between the two by using this curve right? And then if you take the derivative with respect to the solid angle, that's what this partial derivative to omega is. Again, calculus warning. Then you can get the actual candela, luminous intensity candela measurement, lumens per radian, or you can get the radiant intensity, watts per radian. Right? You convert between the two by using the graph up here. But if you take the derivative with respect to area, right, then you can get like an area section where you can get luminance, which is candela per meter squared. This is also called a nit. So your cell phone, they report values of like the brightness of your screen in nits. So that's where this comes from, if you're curious. And then you got radiance, watts per radian meter squared down here, right? And then if you get rid of that directional component, right, you can get like exciting things. You can get illuminescence based on what's hitting it, right? You can get irradiance. So that's kind of how because if you go and try to like look up what is a candela, right, they're going to be throwing around a lot of these terms, right, and you can quickly get caught in like word soup, right? This does a very good job of organizing this word soup and what's actually going on. But I guess ultimately the key takeaway, right, is that lumens are visible spectrum, watts is everything. Okay, so that's the key difference here. Okay, and so this constant, like I said before, right, it is idealized, right? It's not really, you're not gonna be able to get to this value, right? And that's because there's a lot of wasted energy in light bulbs and black body radiation that's not in the visible spectrum. So the one assumption that we are making in this equation down here, right, is that we're just setting this to 1. Well, we're not necessarily setting it equal to 1 per se, right? Where you could just say that we're setting it equal to 1, but in reality, right, this is where physics sometimes can get a little bit difficult, right? Is you kind of have to think like, well, how did they make this 2000 lumen measurement, right? Well, really what they did, right, is that they probably took something, right, and like put it around the light bulb and then measured the number of lumens, right? And by doing that, right, they kind of just combine the constant and this luminosity function into one, right? When they're making that measurement, right, they just kind of reported a value in lumens that sort of took into effect what this graph up here has on it, right? I mean, I don't know exactly how they took this measurement, right? I could be wrong, but that's kind of my inference, right? Is that, okay, they kind of just incorporated this graph into the measurement, right? So that's why this constant kind of disappears, right? And why most of the time in practice, it's not very practical, right? And the other thing you got to realize, right? Well, what happened to the integral? Well, we measured the wattage over the whole sphere, over the whole light bulb. Okay, that's why we have 4 pi down here, right? So this 2000 lumens is over all wavelengths, right? Because part of it we got that measurement by using the graph, right? We got that 2000 lumen measurement because of the graph, right? So we already measured everything over the whole sphere and over the whole spectrum, okay? And so what you can do then, right, is you can just cancel out the 20 watts, right? And then you get 2000 over 4 pi, which is about 160-ish candelas. Okay. And so that's approximately the candela measurement of a light bulb, right? Now things can get more complicated even more quickly, right? Because in our example, we had a fluorescent light bulb. Okay. The thing about fluorescent light bulbs is that they're not a even black body curve, right? They have very specific peaks in the electromagnetic spectrum according to its emission spectrum and its absorption lines. So you're gonna have like a few wavelengths that are gonna be way more prevalent than other wavelengths. We're not gonna run through that example here because that's way beyond the scope of this video, right? But that just shows how this can quickly escalate and become a lot more difficult for you than it really needs to be to get a simple measurement of quote unquote how bright something is, right? Like when I was doing research for this, right, I was like, oh, okay, it's pretty easy to determine how bright something is, right? We've got like the wattage on a light bulb. Well, no, it turns out that there's so many different ways you can measure brightness and intensity, and yeah, like I said earlier, it kind of can become word soup. The good news is that you don't have to do this like hardly ever, unless you're like an electrical engineer or something. So do with that information what you will. Okay. Okay, so with that being said, we're moving on to derived units. I know we're already going on a ways, so we're kind of quickly going to do this and go over what's going on. So, derived units. These are all the named derived units, okay, right? So there's like radian here, right? You got hertz, newtons, pascals, right? What they are in terms of base units, and yeah, like degrees Celsius down here, and then what terms of other SI units, right? Again, as these units pop up in their respective contexts, we'll be talking about them more. But this is what they all are. And most of these, right, are named after people. Like Celsius was a guy, Henry was a guy. Unfortunately, all of them are kind of male-dominated, but you know that's history, and that I cannot change, unfortunately. Anyway, so radian. So radians are used for rotational motion. I got a picture of the unit circle down here. Okay. I mean, what the definition of a radian is that's the arc length on the outside of the circle divided by the radius of the circle, right? And if you want to get to get your radians from degrees, right, you do 2 pi times your angle measure in degrees over 360, and that will give you the amount in radians, okay? Like I said, S is the arc length around the outside of the circle, and then R is radius. We normally start at 0, 0 right down here. That's normally 0, and we go around, right? And we go around from there. Since we're on the radian slide, what I'm going to tell you right now is physicists use radians. It's kind of, I mean, I understand why we use degrees. 360, right? It's a nice divisible number, but ultimately, radians are just better. Get used to radians. You might hate them to start with, but you'll learn to love them, I promise. So just do yourself a favor, right? It's kind of like the Celsius Kelvin thing, right? Like you can never go wrong using radians, but you can go wrong using degrees. So we're going to be using radians. Yeah. So the steradian. So like within the Candela slide, right, I said we're going to talk about the steradian a little bit. So what is a steradian, right? It's a measure of solid angle, right? And what that really means is that, like, if you go back to the previous slide, right, you have a line projection, right, on the outside here. Well, instead of having a line projection, right, since we're doing solid angle, right, we have a area projection. So basically what a steradian is, right, is it produces like an area on the outside of the sphere. It produces like a little like snow cone on the outside, okay? So how I think about the steradian, right, is that you have the total area of the total surface area of the sphere, right, which is 4 pi r squared, right? And then you have the steradian area, right, which is the number of steradians times r squared, okay, right? The idea, and then since the radius of your sphere is the same, right, you can cancel them out, and so then you get 4 pi over n, right? So how I like to think of it, right, is like a percentage of, like, if you have a steradian, what percentage of the area is being taken up by that amount of steradians, okay? So like if you had 100% of the area being taken up, right, by your solid angle, right, the number of steradians you have is 4 pi, because the constant out here, right, is 4 pi, right? That's the maximum steradian amount allowed, right? You cannot have more than 4 pi steradians, at least in most contexts that I'm familiar with. There might be something out there where, like in radians, right, if you go around the circle multiple times, right, you can have 2 pi, then 4 pi, then 6 pi, then 8 pi, right? And you can keep going around, right? I suppose maybe in some motion, 3-dimensional motion thing, you can have more than 4 pi steradians. But for the most part, you can only have 4 pi steradians, okay? But say we only had half the circle, right? Okay, well then we're only having half the area, right? So then we only have 2 pi steradians, right? Or only a quarter of the area is being taken up, right? Then we only have pi steradians, okay? Again, right, it's one of those things where it's like, you don't use this a ton, at least for like my experience with physics. I haven't used this a ton, but when it does come up, you want to make sure that you use it and apply it properly. So that's what I'm bringing up here. Other units, so these are like names that exist for certain units. There's a lot of them, like I said. Don't focus too much on them. Some of them are interesting, right? Like it's pretty interesting. Surface tension, dynamic viscosity, right? Don't focus on it too much. They just exist. We'll come to them as we get to them. The last thing here is that we have, not for the video, but the last thing in this part is that we have units that are not technically SI, but that are commonly used, right? It's like minute, hour, day. Technically not SI, but we use them. Astronomical unit, pretty common astronomy unit, right? You got degrees, arc minutes, arc seconds, right? Yeah, I mean, dude, like an arc radian, dude, would be a really good unit now that I think about it. But anyway, right, one big one though is the liter, right? A liter is equal to 1 cubic deciliter, sorry, 1 cubic decimeter cubed, okay? 1 cubic deciliter, which is 100 cubic centimeters. The reason why the liter is super useful, right, is because 1 centimeter cubed, right, is equal to 1 milliliter. So that's super useful, right? And since the density of water is about 1 gram per centimeter cubed, right, that means that 1 milliliter of water is about 1 gram. Okay, which means that 1 liter of water is about 1 kilogram. Okay, that's the whole reason why this unit exists, is because 1 liter is about 1 kilogram of water. Okay, if it wasn't for that relation, I don't think the liter would exist. Mass, you got tons. Daltons is a chemistry unit for the most part. You got electron volts, and then you got like bells for sound. The other unit that I put here is angstrom. When you do quantum stuff, angstroms come up a lot. 0.1 nanometers. I wish people wouldn't use angstroms and they would just use nanometers, like just say it's 0.1 nanometers, but they don't use, they use angstroms instead. A little bit of a pet peeve of mine, but that's what they do. So other systems of units, we're just gonna do this real quick. I don't have a ton to say about these, but just important to mention. CGS, or centimeter gram second units, okay? So instead of using the meter and the kilogram, right, you use a centimeter and a gram instead. What this is helpful for is it just reduces scale, right? Like a kilogram is a pretty big unit, and then a meter can be kind of long sometimes relative to certain things. And electromagnetism, that is the case where like a meter's kind of long and a kilogram is a lot of mass, right? For like electrons and like the forces that are present there, right? So, so there's a system called CGS. This has largely been phased out, thankfully. I really hated whenever I would read an older scientific paper and they would bring up dynes, right? And I'm like, well, wait, what is a dyne, right? Well, that's unit of force. Okay, well, how many newtons is that, right? So now I gotta go look up what a dyne is and how many newtons a dyne is, right? So it's like, it's super annoying. But energy is ergs. Sometimes if you're like familiar with cosmology, you'll hear about ergs. That's from TGS. Pressure of the barn. Gauss. Sometimes you'll hear about Gauss. The units of Gauss. It's equal to 10,000 Tesla. It's related to magnetic field strength. That's honestly probably the most common one that's still used today is the Gauss, because the Tesla is such a large unit compared to the Gauss. So yeah. And then we have the US customary system. And here's all I have to say about it. Do not use unless you have to. Save yourself time and effort. If they are giving you measurements or asking for an answer for you in feet or inches or miles or something like that, they are just messing with you. They're asking for you to make a mistake, and they are just taking up your time at that point, right? This does not, like, converting between metric and US customer units does not really make you a better physicist. It does not really make you a better chemist. It does not make you a better mathematician, okay? If you know how to do, like, you can do the problem just fine. You can understand all the concepts, and then you can mess up on, like, one little conversion thing by typing it into your calculator wrong, or just, like, forgetting a conversion factor, and then you get the answer wrong, right? That's just a major feel bad, right? Don't use this unless you have to, right? For the most part, I try not to give problems that are in US customer units, because, I mean, multiples of 10 are so nice, and to me, this just, yeah, it's just not fun. So closing out here, is that, you know, these were definitions that we talked about. It's not how to apply the definitions and actually, like, make something that is exactly 1 kilogram, or, like, make something that is exactly 1 meter, right? It's just some definitions and some constants that we're going to encounter down the line that are at least fun to me to introduce in this manner. Okay, it's hard to see major changes in the near future. The second rate is the 1 unit, where I said, you know what, maybe in the next 10-20 years we might see a redefinition of optical clocks. The thing that I will say here is dimensional analysis is a super powerful tool when you're doing physics, chemistry, math, or really any sort of science. Okay, right? Is that if you know the units that are going into your problem and you know the units that you're supposed to get out, right? Making sure that the in equals the out is a powerful tool. You know, as we study equations and things, as we go along, right, you'll always see that the units work out, they cancel out, so you get the desired outcome, right? So if you, like, forget an equation, or you don't remember what something is, right, you can often figure out what the unit is that you need, or the extra variable that you need is, based on using dimensional analysis to make sure that the units are correct. It's a great double check tool. Can help you, again, like, remember things from equations, right? Like, oh, is it squared, is it not squared, right? Use dimensional analysis, it'll tell you most of the time. And then, yeah, more to be explained with, like, the derived units as they appear. Most of the, like, Newton and Pascals and volts and stuff like that, they're named after people, right? And as we encounter those units, I'll probably be doing historical asides on those scientists, just to kind of, you know, go into the history a little bit and see what's going on. So that being said, thank you for tuning in. I appreciate you watching. I hope you learned something. I hope you had a little bit of fun. As I'm just starting out, right, I would appreciate if you liked, leave a comment of improvements, things you think I can do better. Really anything. I mean, I'm just starting out, right? I'm learning about this process as you're learning about physics and chemistry and math. So if you can learn something from me and I can learn something from you in return, that's great, and we can both grow together that way. Of course, you know, if you can subscribe, that'd also be great too. I put my email down here at the bottom as well. You know, if you email me, I'm probably more likely to respond to, like, individual questions or inquiries than if you just leave a comment. As we all know, the YouTube comment section can get a little crazy sometimes. So with that being said, I hope you enjoyed. Thank you for tuning in, and I will see you in the next episode.